and welcome back. In cases where you need to use a push button, relays or switch, or anything mechanical used to close a circuit, like we saw in lectures 15 and 28, we have a situation where the metal comes in contact with metal in order to close a circuit. These contacts are never perfect, and as a result, instead of getting one clean connection, you get multiple ones. Have a look at this example from an oscilloscope which I got from Wikipedia. The vertical lines in the center of the measurement shows that this switch made contact and lost it several times within the space of a couple of milliseconds. If your Arduino was connected to this switch via a hardware interrupt pin, then the interrupt service routine would have been called multiple times. In many cases, like when we just want to switch on an LED, this doesn't really matter. In other cases though, like when we use a 4x4 keypad to enter a password, it does. Any number that you press on the keypad will generate several logical key presses, and you will be having trouble authenticating. This phenomenon is called bouncing, as the voltage of the sampling pin of your switch bounces from one state to the other before it eventually settles. In this lecture, we will look at how we can achieve debouncing, which means how to get contacts to output a clean signal when they are closing or opening. It is possible to write a software debouncer that will do the job. It is not my preferred method since it is tying up the Arduino doing household maintenance and adds unnecessary complexity to your sketch. I'm mentioning it here for the sake of completeness and because the relevant sketch comes with the IDE. So if you go to File, Examples, Digital, Debounce, you can bring up this sketch. Inside the loop, there is continuous sampling of value of pin number 2. The sketch waits for a period of time after the last bounce was detected, and if it exceeds a certain amount of time, which is the debounce delay variable, then the button is interpreted as pressed. To implement this software solution, we had to add 4 variables and 8 lines of code that operate in the loop, and this is far less than ideal. Let's have a look at a simple hardware solution. You can build a simple debouncer by inserting a small capacitor in parallel to the button or switch. In this example, you can see the switch S1 in parallel to a 100 nanofarad capacitor. The Vout is connected to the Arduino sampling digital pin. The capacitor will start charging as soon as the switch is closed, and while it is charging, Vout will be low, as it is connected to ground via the pull-down resistor. Once the capacitor is finally fully charged, and that may take a bit of time depending on how big the R4 resistance is, Vout will be 5 volts, and the Arduino will detect this as high. The mechanical switch will still be bouncing, but the capacitor is now shielding Vout from the effects of this bouncing. This is a much better solution than the software debouncing we saw earlier. However, if the button is connected to digital electronics like a microcontroller, the smooth transition that the capacitor creates between low and high is problematic. In digital electronic, such transitions are bad, but sudden, clean transitions are good. This is not to say that you can't use a simple debouncing circuit with your Arduino, of course. You could, but it is possible to improve and create a clean transition between low and high without much extra effort. What I would like to show you next is a cost-effective solution that takes care of debouncing without adding complexity. Introducing the Schmidt trigger. A Schmidt trigger device is designed for removing noise in digital circuits. They are commonly found in applications where bouncing from mechanical switches is a problem. Logically, a Schmidt trigger will invert an input signal. The following schematic, taken from Wikipedia, shows the function of the Schmidt trigger. U is the original unconditioned noisy signal. B is the output of the Schmidt signal, a nice digital signal without bouncing. In the red boxed area, notice how B is high when U is above the top dotted green line and stays high until U falls below the bottom green line. In the green boxed area, notice how the sample happens even though the U waveform bounces up and down significantly. However, it does not fall below the bottom green line. That's exactly what the Schmidt trigger does. These two green dotted lines mark the high and low threshold levels. The A waveform is the waveform that comes out of a component of the Schmidt trigger called a comparator. The comparator is very simple. It's a kind of binary amplifier that just outputs high when its input voltage goes above a certain threshold, represented by the red line, and low when it falls below the same threshold. That on its own is not very useful. As you can see from the waveform, it doesn't do much to debounce the original noisy signal. To achieve the two green threshold levels that we need for proper debouncer, we create a positive feedback, B, which is also the output of the Schmidt trigger, which reinforces the input to the comparator A, like it's shown in the schematic. To recap, a Schmidt trigger is a device that provides debouncing by conditioning the original noisy signal. The output of the Schmidt trigger depends on the upper and lower threshold levels. Usually, the upper threshold level is 66% of the rail voltage. In the case of the Arduino, that is 66% of 5 volts. And the lower threshold level is 33% of the rail voltage. A commonly used Schmidt trigger IC is the 74HC14. It contains 6 Schmidt triggers. We will use this IC to debounce a push button in this demo.